All right, we'll get started. We have some news and updates. Problem set was graded. Your score should be on Canvas now. You can go on to Gradescope and you should be able to see how we graded it. Where possible, we tried to make as many comments as we could to kind of give some more feedback on individual responses. Overall, the average was a 92, so people seem to do pretty well. There's a couple problems I'll mention. There was 2 multiple choice that had more mistakes than the others, so I'll just go over those very briefly. Reminder that we do have office hours this week. It'll be today and tomorrow to further prepare for the test. They're from 5 to 6. And those Blue Jeans invites should already be going through Canvas. Tentatively, I'm thinking about having the same ones next week at the same time to review for the final as well. Exam is on Friday as well. It'll be the similar kind of layout to what we had on exam 4. It'll be 10 multiple choice, 4 fill in the blank, 2 synthesis, 1 mechanism. It'll be open note and book, but I'm going to more or less treat it like a normal exam. I still intended to be, taken during the time frame as before, but now you would have some things available to reference. Most likely, if you're heavily relying on the notes and books to answer questions, the final has not changed the date. So whatever was originally in the syllabus, to my understanding, is still the same. So yeah, that would be a week from Friday. So that'd be right there. So I think we'd have one more class formally to review, and then I'll have some extra office hours. And I'll probably have those be longer than the normal 1 hour we could probably go over if things are needed. I'll try to get more, a lot of people keep requesting more summaries and more practice problems. And right now, I'm just struggling to get the minimum done. So I'm doing the best I can to take care of everything, and I'll get as much out to you for practice as possible. There will be some sort of review with some summaries that I definitely will have. Just how much more extra on top is what I can manage. The templates for the exam I'll post tomorrow. We're almost to a final version of the exam. I just want to make sure that they're actually going to be the real thing before I put it up so that we don't have any other changes on that end. And other news, I did decide to offer an extra credit assignment. It is, of course, optional. It's extra credit. It'll be worth 10 exam points, and I'll post this after exam 5, and the questions on it would be representative from the entire semester. So whether you need extra credit or not, you can perhaps do it, and that would be some added review. Are there any questions right now about, I guess, logistics of the exam or things like that? If not, I'll review some of the questions from the problem set that I wanted to mention briefly. All right, then I'll keep on scrolling and moving. So for question 1, a decent amount of people missed this question. Where would the exam points go? I think no matter where I would just add them to your final number of exam points. I would say that you wouldn't want to be adding it to your lowest exam because that's the one that's dropped. So I would say, I mean, I wouldn't make it in a situation where they wouldn't help you. So essentially, whatever your exam total is at the end, it would be, say, 10 points added on top of that number. I was thinking the midterms, that's where the point allotment would be. We'll see if something else is needed after. I think that is where people would probably want them to go the most. But I mean, we can try to look at it at the end. I was going to make it essentially, so technically it might be a few. I'll get on to the numbers and figure out what benefits you guys the best. Because the midterm is also out of twice as many points. So 10 points on the final actually may not. I think it'd be essentially the same as adding 10 points to A. Yeah, but if you look at the way at least we add up the number of points, usually it's out of 200 points. So it'd be like adding 5% to the final versus adding 10% to an individual exam. I don't know. This is math. We'll figure out math later. But that is the intention. That'll be available. To get into the problem set review, for question 1, there is a keyword which is racemic. So racemic means it will need to be the products of the mixture afterwards will need to be mirror images of each other. B is not correct because it'll only have one of its stereocenters that can epimerize. So you'd end up making a mixture of the original molecule and also one that has the exact same stereocenter. So this one would end up not changing and it stays constant throughout, while the other one would invert. So you have two compounds that aren't mirror images, then they would be diastereomeric mixtures instead of a racemic mixture. So it's a bit of a detail, and you'd have to remember some stuff from Organic 1. But on a problem set, all these things would be available to you. And number 6 did have a bit of a trick, and it's already highlighted in orange. We run the reaction in ethanol and sodium methoxide. Orgo 1 is too far back. Well, we are in Organic 2, which occasionally will use some elements. And so whenever you use solvents like sodium methoxide and ethanol, but they do not match up to the esters of the molecules, then the first thing you'll probably have before any intermolecular reactions between these two reagents will be transesterification. And transesterification under basic conditions would just involve the attack of ethoxide onto either of these esters to go to the tetrahedral intermediate and then kick out methoxide again. I'm going to reply to a Piazza. It says there's no meeting. I'm going to go send a note to tell the person to keep trying. And they had some questions that they wanted on problem set 5 and 8, and I can get to those hopefully after the other questions we had from Piazza that were posted beforehand. I think they have the wrong link. Sometimes Blue Jeans just messes up as well. Maybe I can quickly get him the link. I don't know if I can do that from... Is this the right link? 2.5. 1 second. I'd like to try to get people in here. Okay, someone else got the right link to him. Thank you very much, class. All right, so I'm going to continue going through. There were some Piazza questions. Oh yeah. So this is something like whenever you design reactions, you always want to match, and you're using something like sodium methoxide and ethanol, and esters are involved, you want to match the solvent to your ester. Because the reason is whenever you run a reaction of ethanol, you have a significantly larger quantity of ethanol than any of the other methyl esters around. And so that'll completely push the equilibrium forward towards the ester of the solvent. So this is something to keep an eye on, both in the context of, doing a question on an exam, or if you're designing a synthesis with methyl or ethyl esters. So there are a few questions. One of this was on enol. I think I replied briefly on Piazza, and I was answering this question in the context of acidity from my memory, but I think I was more talking in relation to question number 1. And this is what I had written out. And just to try to get everyone on the same page of enols. And the question really comes down to, I believe, the comparison of either B or D and how to decide between those two. And that sort of concept can kind of further be broken down to the differences between ketone and ester enolizations. So in general, we want to think about enolization as the thermodynamic stability between two forms. We know that we have a carbon-oxygen double bond that is strong versus a carbon-carbon double bond, which is weaker. And this is one way to rationalize why this equilibrium does not at all favor the forward process and stays primarily in the keto form. If you go and look at something like an ester, and we try to do the same thing, it actually looks really similar at first. Because we have the same CC bond, and this one also has its carbon-oxygen bond. But in addition to this just sort of bond strength argument, the ester also has this really nice resonance donation between the oxygen of like the methoxy substituent and the carbonyl. So this is quite stabilizing. Whenever you go to the enol, though, you don't really have the same, you still technically can draw a resonance structure, but it's not nearly as good. Because along the way, we end up making one that has a carbanion. And so this, whether you draw it from either oxygen, really will not contribute a whole lot. So whenever we go, so you could just use this rationale and apply it to B and D from the perspective of if ketones have more enol content than esters, two ketones will certainly have more enol content than two esters. And for additive things like acidity, these rationales completely work out. Yeah, ester enolates are more basic than ketones and aldehydes as well. So then we'd need to be looking at the charged groups of each one. And in the context of charge, we would need to go and change, I can just change that word to enolate, and I can now make all of these with negative charges on them. So ester enolates are both more basic and they are more nucleophilic. And you can rationalize that as this enolate already has electron density on this carbon. There's more resonance structures you can draw now. But you can see the idea of how we end up having still the same loss in stability. So whenever you deprotonate an ester or you convert it to its enol form, ketones in general prefer the enol form. So it's like, on the whole, you can assume it's going to be more than 95% ketone and less than 5% enol, with two exceptions. The exceptions are when they are 1,3-dicarbonyls, like beta ketos. These end up having about 75%. And that's because of hydrogen bonding. And there's also another resonance structure from this lone pair that kind of helps out. The other instance would be in phenol. Phenol exists exclusively in its enol form. And this is because of aromaticity. So you really need to have something else some other positive interaction to make up for the carbon-oxygen double bond energy stability you're losing in order to push this forward. If enols are nucleophiles and ester enolates are more nucleophilic than ketone enols, wouldn't ester enolates favor the enol form more? So something's more reactive, that usually means it's less stable. So the consequence of esters being less acidic also means that they are going to be more nucleophilic and more basic on the conjugate base. Because it really doesn't want to be in that form. And that's why that makes them, yeah, that's why they're of high energy. And so this is the reason these get a little bit, maybe I think a bit trickier than some of the other analyses of acid-base problems is you really have to consider the ground state of the molecules. So frequently we'll go make the conjugate base and be like, what's the most stable? Actually, that doesn't give you the full picture because we're really looking at where we're starting to where we're going. Because the analyses on both of the ester and ketone enolates look kind of similar. And this also goes back to sort of the reactivity, the same concepts of why the neutral compounds, a ketone is more electrophilic than an ester. A lot of these sort of concepts kind of connect to one another. But in the end, if you want to just correlate enol form to acidity, usually that will get you there 100% of the time. So if one of these makes more sense, those two trends correlate. Okay, there is another acidity question. I know some of you guys want more acid-base questions, and I'll try to pull up some more. If you actually go back to some of the early exams, we were talking about some of these acidity concepts way back then, just from a reactivity perspective, and could be useful to review. Exactly, because they are more nucleophilic, if something is more reactive, that probably means that it prefers to be in a more stable form. Absolutely. And we're looking, and this is a question from the recommended problems in the back of the book. This is 1815, question C. And we're supposed to rank the acidity in different order. So any of the practice problem books, I think it's always a good idea to, one, go try to come up with your own solution and rationale, but then always rely on a handy table. So I pulled these from the table in our notes from topic 1. Perhaps go and check yourself. And so, and I think some of the specific questions between each of these, perhaps we can go and get out of the way. Usually alkanes, these hydrogens are not acidic at all. We never see these becoming deprotonated unless they have a carbonyl next to them, or they're on something like an alkyne, and in that case, they're not an sp3 hybridized CH bond. And if you go to the table, you'll see that it is 60. And they even say about 60 because I think these are pretty hard to measure experimentally. So we can say this is going to be, about 60, and nothing really will be less acidic than this. This is sort of our complete far end of the spectrum. If we go into something like a carboxylic acid and an alcohol, these become rationalized because we have, in the case of an oxygen, we have 2 oxygens to put the charge on versus just 1 for an alcohol. This results in greater stability of the conjugate acid. So I think comparing an alcohol and a carboxylic acid makes some sense. The one that is sort of the outlier, and we haven't talked about much in class, is the nitrile. And so we know that it's an electron withdrawing group. We saw it in some beta keto examples in class, but not too many. But we're going to use the same sort of analysis. So we're still going to go, and we can imagine making a conjugate base. Actually, I'm going to erase this so I can draw an arrow. So if we make the conjugate base, we end up with a nitrile with a negative charge. And this also has a resonance structure. In a way, it's kind of like an enolate resonance structure because we have a pi system next door. And we can put the negative charge on a nitrogen. Usually putting negative charge on a nitrogen is not very great, but right here in this form, it would be sp2 hybridized. And so that will be more electronegative than your average just, tertiary amine. So this one is not bad, but it's still not oxygen. So if we're trying to figure out where does this molecule fit relative to, say, ethanol, which is probably the hardest comparison, without looking and referring a sheet, I would probably want to go and be like, okay, what is something that is somewhat similar that I do know? And so The ketone, I would say, is the closest thing we have in similarity, right? Because this has some similar types of resonance forms. We can go and we can actually put it on a more electronegative atom. These are two that are maybe a bit more directly comparable. And if you know that this pKa is around 19, and 19 is greater than 16, then we could probably rationalize that acetonitrile is going to be less acidic than a ketone. I would say they're pretty similar, but they has, in terms of resonance, it has a worse heteroatom to put the charge on. But at the end of the day, I would say I wouldn't put this question on an exam because we haven't talked about nitriles too explicitly. But I think you could try to use some of the sort of reference points we have to get to the right place. There are some things that I think are hard to justify or rationalize in your mind, like things between an alcohol and ketone being the number one that I think, why is it that they both, like if you look at an alcohol, you put the charge on one oxygen. In an enolate, you put the charge on an oxygen and you have resonance to a carbon, and that ends up being a penalty. These are hard to justify without more information. And so that's why we have a pK, like a few pKa's to keep in mind, that we don't necessarily have to directly rationalize these two numbers. We can just kind of rely on this one being a little bit higher than this, and then use other information to come to decisions. So hopefully that clarifies. So yeah, nitriles are actually closest to ester in acidity. They're still going to be pretty electron withdrawing and still have decent resonance stabilization. Ooh, questions. This is fun. So these are some questions from the book, and we can go through them. There is an electrophile that we have not seen before, but this is, I think, a situation where we can go try to imagine what is going on. So if we have an aldehyde plus LDA, there's only one hydrogen that can be deprotonated, alpha. The LDA will take this proton to make an enolate. And now we're going to add in an electrophile. And no, I don't think we talked about this electrophile at all. This is ethyl chloroformate. But given what we know about the reactivity of a carbonyl molecule with a chloride and the reactivity of enolates, we can make a safe assumption that the carbon of the enolate will attack the carbonyl of the chloroformate. This will make a tetrahedral intermediate. That has a chloride on it. And we have the choice of either a chloride or an ethoxide leaving. Chloride, of course, will be our best option. And this ends up being a reagent to make beta aldehyde esters. And potentially, if there's still base around, we would it would further deprotonate and then reprotonate again. But this is the overall logic for that problem. For F, this is going to be our haloform reaction. So if we have sodium hydroxide and a methyl ketone in the presence of some sort of halogen, we're going to make an enolate. Or I'll try to make an enolate. The iodine will be able to react with the carbon of the double bond. I probably would specify there is an excess. This would be something that would be pretty difficult. Yeah, so I'll comment on that on the, it's not super black and white actually. I would think you would get a mixture because I think you could rationalize that the products could actually react a little bit faster than the starting material. And this will keep going or at least the way whenever I saw this problem, I assumed it was the haloform reaction. And you need to get 3 halogens on the carbon in order to make it a good leading group. I'm not drawing out all the arrows, but I want to draw out 2. I'll just say keep going to give you the carbon with 3 iodines on it. The sodium hydroxide will attack. The Ci3 now is going to be a pretty stabilized leading group because we have 3 electronegative atoms that are good, or especially polarizable atoms that can kind of take on that charge. And we'd get out benzoic acid. Benzoic acid, of course, would be quickly deprotonated, and then they add H3O plus to just go and make the acid again. So the reason I would always be using, on the exam, I would always specify an excess, or at least 3 equivalents of iodine, bromine, these sorts of reagents, is because once you get to the first intermediate, this is probably, oops, I didn't mean to have 2 iodines. This hydrogen is probably more acidic than the starting material. So it's possible you get sequential reactions. As you get 2 iodines on there, then the question is, how slow is the last iodination because it's more hindered? But I would expect if you try to use 1 equivalent, you would get mixtures. Because usually we'll have an excess of sodium hydroxide. So as you do this reaction, you make benzoic acid, and benzoic acid will completely react to make the benzoate salt. But at the end of the reaction, you have a benzoate salt, and you need to add acid to get it back into the acid form. Because this is all in the same reaction, and this is the one just afterwards at workup. Cool. We still have some more problems. I'll keep moving through. So the question on this problem was, what does prolidine do? I could get to the answer probably by using, LDA and benzyl bromide. And yeah, you can do that. And the only time I would say that you'd probably want to be using an enamine specifically is probably if I put an enamine in a problem. There's good questions about reactivity, and that reinforces good concepts. But the enamine here, this is our Stork annulation. I don't know if I called it that. I think it's in the very last lecture, lecture 30, on enamine reactivity. So this would be with tosic acid, a little bit, and probably something to drive off the water. And then the enamine will be nucleophilic, and it can react with things like benzyl bromide. I'll draw that out just so that everyone sees it. Where the Bn is benzyl. This first makes an iminium salt that is positively charged, and we've added on our new group. And then we add water to work this up, and it hydrolyzes the iminium. So I think I went through the general mechanism of this last time, in last class, so probably won't be any more explicit than that right now. So in this question, there was confusion on how the removal of the carboxylic acid under heat occurs. So in this problem, the solution is to use a methyl acetoacetate or some other acetoacetate. And you'll deprotonate this. It'll be able to alkylate this bromide. Then we're going to have a very fast second alkylation after the first one, because it'll be intramolecular. I am skipping steps. I want to get to where the question is. And I'm going to just draw this in this form rather than the enolate. If it helps you guys to think about enolates in the carbon form, I'm okay drawing them that way. If I ask you what's more stable between two resonance isomers, you should be able to come up with the one that has a charge on oxygen. But for mechanisms, it's sometimes more useful to draw it in the carbon form to keep track of all of your numbering and atoms. And we get to this situation. And then you can react this with either sodium hydroxide and work it up with acid, or you can just react it with H3O+. Someone asked that on Piazza, and you can. It's actually just a little bit easier to hydrolyze things under basic conditions. So that's why people operationally will do this. We can say H3O+ will hydrolyze the carboxylic acid. And to get this rearrangement to occur with loss of CO2, you don't need to have two carboxylic acids. All you need to have is another carbonyl. So this carbonyl will also be able to make the same cyclic transition state to lose CO2. Briefly go to the enol form that tautomerizes to the product. Yeah. How to turn the ester into a ketone. Oh, I just misdrew. Thank you. Yeah. So this methyl started as a methyl ketone, and I just didn't continue to draw it throughout very well. I apologize. Put my ME back on. Yeah. This would be the acetic acid ester synthesis. There's some questions on some of the extra synthesis solutions. This question specifically is asking about the last step with sodium hydride and methyl iodide. I won't draw out the whole molecule again, but in general, if you have some sort of alcohol, you react it with sodium hydride, we're going to make an alkoxide. And if you have something like methyl iodide around, this will just do an SN2 reaction to make a methyl ether. This is the Williamson ether synthesis. This goes back to, once again, an earlier section on alcohol reactivity. Got just one. All right, this is the last of our Piazza questions. And then I can go back to the problem set questions that were just posted on Piazza recently. What would happen if you didn't turn the carboxylic acids into esters? So if you tried to do an aldol with a carboxylic acid directly, it pretty much wouldn't do anything. If you try to do the aldol, any base you choose, whether it's methoxide or anything, you're going to make the carboxylate salt, and you will not be able to further deprotonate this because you really need to make an enolate. And so you won't be able to deprotonate twice because this is not acidic enough. So the dianion is much higher energy than your average enolate because of electrostatics. This is going to be very high energy and is not going to be able to deprotonate again. Yeah, I can get to the carbonyl case in a second. The other way you can do aldol reactions is under acidic conditions, and even that won't work out very well. Usually you won't be able to make enough of the enol form of the acid, and it won't be able to do an acidic catalyzed cyclization either. There is a good suggestion on Canvas to turn the esters into an aldehyde, and that actually, you can come up with an even faster solution to this. I can draw that out pretty quickly, I think. Let me cut and paste something. People want to see it. So I won't draw all of them, but I'll go and do the abbreviated version. We still need to make the bis aldehyde. So this could be lithium aluminum hydride followed by PCC. And then if you do the aldol cold, like 0 degrees Celsius, you can make this. And you can finish this up with ammonia, catalytic acetic acid, and sodium cyanoborohydride for reductive amination. So this is another option. Once you get into some synthesis problems that have more things changing, usually there's more options and ways to do them. I will write the first one that pops in my head. I may have actually had this as an answer in previous years. I don't know. Could be. All right, I'm going to try to address some of the Yahtzee question that was coming up. Oh, he still wasn't able to get on. I cover number 5 and number 8. So there was questions about number 5 and number 8 from the problem set. So let's go grab those problems and take a look. Okay. This one is number, we wanted 5. I'll do 5 first. So this involves a few steps. We have LDA, so it's going to deprotonate the least hindered hydrogen. That ends up being this hydrogen. It goes up. And this once again will be a pretty much irreversible reaction. So we're going to make this enolate. We're going to add it to cyclohexenone. Enolates are soft nucleophiles. So we're going to expect this to add 1,4 to the carbonyl. To make an intermediate enolate that with ammonium chloride we can go and make the product, which will be D. So this is a Michael reaction. And I think the main parts of this question that are being tested are, do you know which part of the molecule LDA will deprotonate? And also, do you know from this enolate where will it attack the cyclohexanone? Because it's electrophilic at both C2 and at C4. 1, 2, 1, 4 additions. All right, and the next question is number 8. We're gonna review. And this is another Aldol type reaction sequence. I'll drag this to the next page just because I want to have enough space. So now we go and look at the start of this reaction. We have 2 aldehydes, so we want to think about an aldol reaction. One is non-enolizable, so we know that we're going to have selectivity in the cross-aldol reaction. And we have heat, so we know we're going to expect the elimination to take place, that E1CB. So this is our initial enolate. I'll skip a couple steps, but I want to draw the main arrows just so that everyone can follow and keep track of carbons. So this will attack. I'll draw the product after a proton transfer takes place. We ended up making this compound first. More sodium hydroxide will be able to deprotonate this enolate and eliminate in the E1CB. This gives our alpha beta unsaturated aldehyde. And now we're going to add in ethyl lithium. This is a hard nucleophile. So this will not add 1,4. This will add 1,2. And this is somewhere where I updated the question a bit online to add in, I believe, a workup step and also add a 2 to chromic acid. Those are the 2 typos that I missed and seem to still be on my iPad. But nonetheless, this will end up being protonated on workup. And then chromic acid will oxidize the secondary alcohol to this molecule. And this corresponds to D. We did it. Sure. So if we want to review hard versus soft, hard nucleophiles, soft nucleophiles. So when we have hard nucleophiles, these will always do 1,2 addition. Soft nucleophiles would do 1,4 addition. And this refers to an alpha beta unsaturated carbonyl compound where we number 1, 2, 3, or 4. We can draw an arrow for a hard addition. It's going to attack here. And a soft nucleophile, let's make it a nice, I want it green. Green's a soft color. I like green. It's going to attack the 1,4 position and push the arrows this way. When we think about hard, this means that we essentially have very reactive electrons. It means there's probably going to be a lot of localized high density charge. And this correlates to only a handful of reagents that we've learned. Things like lithium aluminum hydride, the reducing agent that'll react with almost anything. Organolithiums will always be hard reagents. Grignards will always be hard reagents. Organometallics, you can't make that generality because on the soft side, we have things like cuprates. Remember, cuprates didn't even add into ketones, but they will add into the carbon of an alpha beta unsaturated ketone. So copper is a much bigger atom. It makes much more covalent bonds to the alkyl groups, so we can imagine this being less like a carbanion with a lot of very localized charge. These generally will be highly stabilized, such as by resonance. Because of this, this includes all enolates we'll talk about. And this is generally true. If you have a neutral nucleophile, like an amine, it'll react this way. Any type of thiol or thiolate. And this is because if you consider the size of oxygen versus the size of sulfur, it's bigger. So whenever it has a negative charge, it's able to disperse it over the surface a little bit better. But these, I would say these are the ones that you probably want to remember, and probably the rest will be soft. There's actually, so while I draw a hard line here, of course, the reality is a bit gray. Things like sodium borohydride actually usually give mixtures, and there's a lot of reagents that aren't strictly one or the other. So that's why I would recommend if you need to do a reduction 1-2, really stick to lithium aluminum hydride. If you want to reduce the double bond, I would go with another method like palladion carbon that will hydrogenate double bonds. The conditions to reduce carbonyls with hydrogenation, that's pretty specific for those rainy nickel catalysts under high pressure. I saw a few people putting that answer on the problem set, so you do get selectivity with palladium versus other metals on hydrogenation reactions. Cool. I think I got through all the Piazza questions. That's amazing. There were quite a few today, so hopefully I was able to address everyone's questions. Are there any other things people want to know about? If not, then maybe I'll see some of you this evening or tomorrow evening. I'll keep trying to work on getting some more materials uploaded. I'll get the templates definitely uploaded tomorrow, so that way you can have them for to prepare if you are going to go that pathway. Otherwise, everyone have a good one, and I'll see you later.